was this. We actually considered a frame of reference, and then we had got another frame which was moving with the, let's say, a velocity v with respect to the fixed frame. So we do had a primed system and an unprimed system. Okay, so if you basically consider the unprimed system on this side, it can be written in terms of primed system, which is on this side. So this is the prime part. Okay, so in primed part, we saw that if you write down the acceleration, there are 4 parts to it. First term is the acceleration of the primed system. Okay, the second, this term is basically the centripetal acceleration. Okay, this is basically the Coriolis acceleration, if you remember. Okay, and then this part is actually nothing but the acceleration of the primed frame with respect to the unprimed frame. So these were the 4 things that we have seen. Okay, the last class. And then the centripetal acceleration, okay, you know, it's always directed towards the axis, and you know there is something which is also called the centrifugal part. Okay, so what I wanted to tell you today is something additionally in terms of Coriolis force. Okay, and just look into some specific cases. Okay, so at the outset we have to remember these 4 parameters. Okay, 4 acceleration values, and based on this we are just going to do some kind of conclusion here. Okay, the first part is of course centripetal acceleration, and this is something which we have already discussed. It is directed towards the axis and its magnitude is this. Okay, and what we did was we take omega cross r, and we know omega cross r is perpendicular to the plane containing omega or r. So by vector triple product, if this is omega or r, the angle between this and this will be 90 degree. So we know this is omega cross r sine of theta, right? So sine of 90. So 90 is 1, so it is omega cross r. And omega cross r is nothing but omega sine theta. So you just write it down as omega square r sine theta. So this is what we have seen the other day, and then we have found out what is called the centripetal acceleration, simpler form. Okay. Today what I'd like to tell you is some more theoretical part. Okay, just conclude this, very important. So the second term that I said was actually nothing but the Coriolis acceleration. So this term 2 omega bar cross t dash r bar dt is the Coriolis acceleration. Now the question is, what exactly do I mean by Coriolis acceleration? How do I understand Coriolis acceleration better? What I can do is this. Take this a very simple example. Suppose you are in a circus, okay, and then there is some kind of platform, okay, which keeps on rotating. So there will be someone who will be pushing it at this from this edge with a velocity v. It might be if you want to increase the angular acceleration, angular speed, there will be someone who is also pushing at the speed v, because of which this is rotated. Okay, now you are here sitting here, and your friend is sitting here, and then initially when this is not rotating, when this is not rotating, your friend is throwing a ball to you and you can catch it directly. Okay, you can catch it directly, no issues. But what happens is once it starts rotating, if your friend throws the ball now, you will see as if the ball is coming and following a curved path. That is Coriolis acceleration. This velocity keeps on changing, and when the ball is thrown, it will basically follow a curve, and that is Coriolis acceleration. The question is, when there will be no Coriolis acceleration? Of course, if this term is 0. Okay, sorry, not this term. This term is 0. What is this? Angular velocity, right? So this will not happen if the ball is not thrown. If you are holding this ball in your hand, or your friend is holding the ball in your hand, then the term of Coriolis acceleration becomes 0. It vanishes. This will become 0. So there will be no Coriolis acceleration. Okay, so this is what we are going to look into now, and as an argument. Okay, but if you consider this d omega by dt into r is nothing but the acceleration produced by the x prime system with respect to the unprimed system. Okay, so these are the 4 terms that we had, and I told you that I'll give you something extra on Coriolis acceleration, and this is the example I want to discuss. Okay, let's just do a bit of Newton's law discussion here. And if you talk about Newton's law, force is equal to mass into acceleration, right? And This is the force that we're talking about. And if you consider this term now, the acceleration that we just now got, we can just multiply m into whatever a we have. So we have got one term this, the second acceleration was this, okay, and centripetal acceleration of course, and then we had got this, okay, the Coriolis acceleration, and then this is the prime with respect to the unprimed acceleration, and multiply each of them with mass, you are going to get force. And what you get the force, you can easily say what is this? Coriolis force. So you know there are some trick questions. So you know acceleration multiplied by mass, I'll get the force. So that's Coriolis force, not a big deal, right? But you know, if basically considering a normal acceleration, which is mass into acceleration, the other part of the acceleration is going to reduce the force here. Okay, what do I mean by this? See, this m into d2 d dash square r dt square is nothing but the acceleration in the primed system. This is the acceleration in the primed system. And if you do the maths, you know F is on this side, the other term will come on this side. So it will be the original force minus all the forces which are created because of the different components of acceleration. Okay, so you will F minus of this. This is clear from the mathematical picture. Okay, so this is what is happening. So in the prime system, the force will be less because of all these accelerating components. And this acceleration component, it doesn't mean that it will exist every time. As I said, this term can easily become zero when the body is in not in having a velocity in that moving frame of reference. Okay, so this should be clear. So what we say usually is that this particular term, okay, can be put as the effective. This particular term can be written as the effective force, and this is the effective force. Okay, just to simplify things a bit better, what we can do is we can take d dash r dt as v dash. Okay, so this term will just replace. So we can just simply write down as minus 2m omega cross v dash. Okay, this term minus m omega cross r cross omega cross r. Okay, this term, and then finally this term. We'll write down this term, okay, and then we have this. So what is this? This is the Coriolis force. So this 2m omega bar cross v bar dash is called the Coriolis force. And now I think whatever example I have given, you can just relate to it. What is this v dash? V dash is the velocity in the primed system. If the body or the ball, that example I've given, is not moving in the primed system, you cannot have a Coriolis force. You cannot have a Coriolis acceleration, you cannot have a Coriolis force. So that will become zero. Okay, that's very important. And of course, if the Coriolis force exists, what will be its direction? Okay, so I think this I already explained, but then let me just explain it again. If you have got three vectors, A cross B cross C, okay, B cross C, these all are vectors. Then whatever result you get, this will be another vector, right? Let's say D. Okay, this vector is definitely going to be perpendicular, okay, to both B, okay, and C. Okay, so maybe I can just put a B here. So this vector D will be perpendicular to vector B always. So you see, if you are considering a cross product of omega and V dash, the resultant of this, the resultant vector that you get, that means the force that you get, which is a vector quantity, will be perpendicular to the plane containing omega and V dash. Okay, so you know this is how the triple product works. Okay, so you have got omega and V dash here. Okay, one is omega and one is V dash. Okay, omega V dash. Then the vector F or the Coriolis force will be along this way, perpendicular to both this and this. So this is an important conclusion. Okay, I don't know what kind of question can be framed from this because I have not really checked the questions from this part. Okay, but then if you go for any kind of competitive exam, they do ask you some tricky question. Don't worry about me. I might not give you any tricky questions from here. Okay, but then it is important to understand. If you understand this, I think definitely you can use it later. Okay. And what happens is when the particle is fixed with respect to the rotating frame. So this is exactly the argument that I said. The Coriolis force is zero. Another point is, for a uniformly rotating system, omega is constant. Okay, the angular velocity will be a uniform rotating system. So this component can also become zero. We've got one more for acceleration, right? D omega bar dt cross r bar. If this part is constant, d omega by dt will become zero. Okay, so this entire part will be zero. So if it is uniformly rotating, the example that I said, you take a v and you are applying this v at every point, okay, and then this is uniformly rotating. There is no jarring or something because of which the velocity might reduce or increase, it might decelerate or accelerate. Okay, if there is no acceleration, definitely the component will become zero. You can get rid of this component also. Okay, so you can also write down this. I think I don't need to go back. You can also write down this acceleration as f by m. I think this is also very simple. Acceleration is equal to f by m minus omega cross omega, provided that component is there, and then 2 omega cross v, Coriolis force is there. Okay, this is under the condition that the rotating frame, the velocity is constant. Okay, it will vanish, and the remaining two terms will be there. Okay, so what I'm doing here is I'm just simplifying things. It should not be very difficult to understand. Okay? Same thing here. And you know, whenever there is a force because of the Earth's attraction, you have got it as g, right? Acceleration due to gravity will be g. So if the Earth is rotating, okay, you do have the involvement of other components. The centripetal acceleration will be also there. So if you consider the acceleration due to gravity of the Earth, okay, the effective acceleration due to gravity of a body which is moving will be nothing but g minus omega cross r. Okay, so what I want all of you is try to understand this, try to sleep over this. Okay, and you will easily understand the concluding remarks for this particular chapter. So these are the important points, and I think one more thing I can talk about is the value of this omega cross r, that is centripetal acceleration at the equator. Okay, so if you consider centripetal acceleration and multiply by mass, you get the centrifugal force. So m omega square r bar. Okay, we have this, and then the magnitude, if we just consider m omega square r sine theta, this value will be maximum when it is at the equator. Okay, because you know sine theta comes off because of the angle between omega and r, the angle between angular velocity and the distance from the center. So the angle between the angular velocity and the distance from the center is 90 degree at the equator. Okay, a bit of geography here. So if it's 90 degree at the equator, this will become sine 90, that is one maximum value. So omega square r will be maximum. Okay, and it can be found out experimentally because we know what velocity the Earth is rotating. We also know the radius. The value is 3.38 centimeter per second square. Okay, so that's the value of centrifugal force. Okay, sorry, centrifugal acceleration, centimeter per second square. Okay, of course, if you multiply it with of the Earth, you can definitely get what is the centrifugal force, right? So that's there. And then this is actually 0.3% of the acceleration due to gravity. So you know acceleration due to gravity is 9.8, right? All practical purposes, we usually take it to be 9.8. You can always change it. Okay, so this is meter per second square. So I think I just missed out on the unit. Okay, there is some mistake there, but anyway, this should be, I think it should be meter. Oh, sorry. No, this is centimeter. This is 3.38 centimeter per second square. Okay, just do the calculation. I don't think it's very difficult. I've just written the values here, not done the calculation. But then this value is 0.3% of the acceleration due to gravity, a very small fraction of the acceleration due to gravity. So you know that the acceleration of the gravity due to gravity at every part of the Earth's surface won't be same. Okay, and this can be estimated from this idea of centrifugal acceleration or centrifugal force. That's it. Okay.